Hello, everybody. My name's Nick Eyles. I'm a geology professor at U of T Scarborough, and I was trained many moons ago, back in the Precambrian, in glacial geology. So I've spent most of my career looking at glaciers, ice sheets, studying modern ice masses, and then coming back to Canada and trying to explain and interpret what we see in terms of the ancient glacial geologic record. And it's important to study ancient ice ages in Canada because we live on glacial sediments. Many of you who have a well in your backyard, you'll be drinking groundwater that's in glacial sediments. Your house will be built on glacial sediment. And our economic success in Canada has been built on finding minerals in the Canadian Shield and using experience with ice sheets and how they transport sediment to locate buried, hidden ore deposits. So it's an important field of study in Canada. And as a geologist, we use an approach called uniformitarianism, where we go and look at the modern ice sheets, and then we come back to Canada and, as I say, look at the ancient record. Now, the whole field has been transformed just in the last 5 years by a new technology called LiDAR. I'll explain what that is fairly shortly. But it's equivalent in many ways to the introduction of the microscope in the Netherlands in the 16th, 17th centuries. And very simply, we can see an awful lot of stuff on the ground, which we couldn't previously. And if I can be politically incorrect, I always refer to that as a Christopher Columbus moment, because we are visiting a new land. We're seeing stuff for the first time that no other geologist has seen. So it's pretty exciting. And there is the prospects, I'll explain right at the end, of automated mapping using artificial intelligence to do all sorts of clever stuff. So ice ages, glaciations, we've had several in Canada. This is what the world looks like during an ice age. This was the last one about 20,000 years ago, and we call that Wisconsin glaciation. It's named after a type site in the US. And thick ice, and when I say thick, I mean ice that's several kilometers deep, is covering up to 40% of the Northern Hemisphere. Toronto, I should say Owen Sound, would be under ice about 1.5 kilometers thick. So if you happen to glance outside on this rather sunny afternoon when I'm recording this, look up to the clouds. That would have been the top of the ice that's burying Owen Sound, and it would have been flowing down into the States. The ice sheet over Canada is the biggest and the best. Accounts for about 30% of global ice volume during any one ice age, and we refer to that as the Laurentide ice sheet. So it's a major player in the sort of global ice budget. This is an old-fashioned look at the ice sheet, and there's one major ice sheet called Laurentide, and then there's a number of subsidiary smaller ones. One over Newfoundland. Newfoundland's always a little bit different. There's one over Greenland. There's one up in the Arctic, and then there's one over the Western Mountains called the Cordilleran ice sheet. And if you think of them like eggs in a frying pan, they have that sort of domed shape, and they flow outwards under gravity. And the arrows give you the generalized flow directions. That's a simple model, and as I'll finish this afternoon, it's now out of date, primarily because of new imaging of the sediments that ice sheet left. So that's the old picture. That's at about 20,000 years ago. That's what we call the last glacial maximum, the coldest part of the ice age. And Southern Ontario is quite famous in terms of glacial geology because, unusually, we have a record in the Toronto area, Toronto being the center of the known universe, of course, of two ice ages separated by warm climate sediments, and that's referred to as an interglacial. So if you think of a sandwich, and the lower part of the sandwich, the bread, is what we call the penultimate glaciation or ice age, and that's referred to as the Illinoisan glaciation. Then we have warm climate interglacial beds, and then there are deposits of the last glaciation on top. So if we look on the left-hand side of the diagram, that's what we call a stratigraphic column. And according to geologic convention, the oldest stuff is always at the bottom, so you'll see bedrock. And that's in the Toronto area, the Georgian Bay Shale. And sitting on top of that in green is the famous York till. And till is an old Scottish word referring to the very poorly sorted bouldery deposits left by ice. So York till, and you'll just make out to Illinoisan glaciation, and that's, you know, we don't have a very good idea of the dates, but it could be anywhere from about 135 to even 200,000 years ago. And then the Don Formation, which is famous because it contains fossils of warm, loving trees and other insects. Insects are very useful, actually. They're quite widely preserved in sediments, and they have very restricted tolerances for climate, so we can derive quite precise paleoclimatic data from insects in old sediments. And then as we go up the column, you'll see Wisconsin glaciation labeled at the side. There's a paleotemperature graph added as well. And to cut a long story short, it gets colder. There's a whole bunch of deposits which record proximity to an ice sheet that's growing over Quebec and Labrador. It's advancing down the St. Lawrence Valley into the Ontario Basin, damming up lakes. And then on top you'll see another word, till. We've had that before. Northern till, Horton till, and that's the last glacial maximum. So that's when ice is over Toronto, about a kilometre thick, and then it backs out and we get a whole series of post-glacial deposits. So if you get the opportunity, if we have this vaccine in our arms by next summer, you can take a trip down to Scarborough Bluffs and you will see ice age deposits preserved there. And the jewel in the crown is the Don Valley Brickyard. It's now called Evergreen Brickyard, and there is a geological display in the buildings there, and it's famous in North America because it has the York till, the older ice age deposits, the warm climate interglacial deposits of the Don, and then the last ice age deposits on top. And this is really unusual because if you think about what an ice sheet does, it scours away all pre-existing sediment. So it's very unusual to have these older sediments preserved. And you'll see on the left there the most famous character, the fossil that's preserved in these warm climate beds, and it's a giant beaver, and it would have been the size of a Labrador or something. Thankfully they're extinct now, but that's the most famous symbol of the Don beds. And the geologist behind me has his hammer resting on the boundary between the older ice age deposits and the warm climate deposits on top, and that's quite a marked change in global climate too, and that's completely unusual in North America. And in most places you only have a record of the last ice age. So Toronto is famous for a number of things, of course, but for its glacial geology, because it records a penultimate ice age followed by a warm interval, and usually all that stuff's been scraped off elsewhere in North America. So the question arises, and this is a question that no doubt many of you have pondered over, I am sure: how many ice ages have we had? And you won't find the answer on the land surfaces because everything's scraped away by ice sheets. So you have to go out to the ocean where there's continuous sedimentation in deep water, and I'm talking about several kilometers deep water, and it's necessary to drill through those sediments, collect cores, look at the fossil material. And the fossil material is very useful. It gives an idea of the conditions in the water column, temperature. And there's a graph on the right there that has a sawtooth pattern going from blue on the left, and these are ice ages, and red on the right of it, which are interglacials, warm intervals. And if you want the time scale, that's about the last 2.53 million years. And this is an interval of time that geologists call the Pleistocene. So we can talk about Pleistocene ice ages. And if you've got the time and the inclination, you can count up the number of blue spikes. It's not as easy as it looks, because there are sub-spikes within each ice age. That is to say, we often get warm intervals within ice ages, when ice might retreat a little bit, but it's still an ice age. So if you do that exercise, you end up with about 52 ice ages. So now if anybody asks you, do you know how many ice ages there have been in the last 3 million years? You can say, yeah, there's at least 50. Now, when I was a student, a long time ago, we were taught that there were only 4. And my grandfather was taught that there was only 1. So there's been a huge advance in understanding paleoclimate of the last couple of million years. So you'll see the names on there: the Wisconsin glaciation, that's the last one. Illinois glaciation, that's the penultimate one. And then the Sangamon interglacial on the right. And again, if anybody asks you what's the name of the modern interglacial that we live in, it is of course called the Holocene, which is Greek, it's not American, and it means the wholly recent time, most recent. And that's really the last 10,000 years. So I explained earlier that the maximum of the last ice age was about 20,000 years ago, and disappeared, gone from Owen Sound, gone from Toronto, by about 10,000 years. And that the last 10,000 years are called the Holocene. So this is what our part of the world would have looked like about 20,000 years ago. I'm sorry I didn't indicate Owen Sound on there, but ice would have been sweeping down to the south into upper New York State, down into Pennsylvania, and as I say, it would be more than 1 kilometer thick. How do we know the direction that the ice took? Well, there are distinctive landforms called drumlins. And a drumlin resembles a rowboat that's been turned upside down. And you can recognize a bow, that's the sharp end that's on the left of that hill, and then the stern to the right. And that allows the direction of ice flow to be mapped, and that's been done for all of Canada. It's very important information if you're interested in finding minerals up on the Canadian Shield, because the shield, the rock, is buried by glacial sediments, and we have to prospect for minerals, not by mapping the rock itself, but by taking samples from the sediments, analyzing them for targeted minerals. And then if we find an anomaly, we then have to say, well, we have then got to pose the question, well, where the hell did it come from? And so we use our knowledge of ice flow directions to say, well, I think it's to the northeast or the northwest. And then we do a whole bunch of geophysics to identify potential targets, and then we go in and drill. So it may sound very simple, determining the direction of ice flow, but it's very, very important information. That's all from drumlins. This is near Peterborough. It's just east of Peterborough, and this is an area that's referred to as the Peterborough Drumlin Field, which may be familiar to some of you. And you can see a great armada of upturned rowboats, in other words, a drumlin field. Actually, it's called a swarm of drumlins. I don't know why. But you can see, I hope, that the direction of ice flow was from the northeast, that's top right, down to the bottom left. And that's rather an old map now. We now have LiDAR available, and we can now get a lot more information out of that area. But that's the Peterborough area, sometimes referred to as the Trent Hills. If you go there, you follow any of the roads, you go up and down over these successive drumlins. So that's what an ice sheet does when it flows over sediment. It leaves these streamlined mounds called drumlins. Right, now the world's a different place than what it was 5 years ago, because in another 15 or 20 years we're supposed to be driving autonomous vehicles. I'm not sure I want to. I quite like driving. But if you're going to have an autonomous vehicle, that vehicle has to know exactly where it is and what's around it. And there's all sorts of military applications as well. So the big question now, the big need now, is to map the Earth's surface in unprecedented detail so we can locate vehicles, etc., with hitherto unprecedented precision. So this is where LiDAR comes in. This is light detection and ranging. It's using light, could be visual light, could be infrared, and it's all based on two-way travel times. So there's an instrument in this plane. We also use drones. Miniaturization is the word of the day. So what could be fitted in a suitcase 5 years ago can be held now in the palm of your hand and put on a drone. But light is emitted from the source up in the sky. Light goes down, it's reflected back off the ground surface and then back to the source. And the two-way travel time gives you elevation of the source, and you can figure out the topography. And this is now done routinely. It used to be fairly expensive. It's now coming down in cost like everything else, but it's very rapidly evolving. So this is what's happened in the last 5 years. But the 5-year-old data is on the right, where it says 30 meters, and that's a reference to the resolution, the horizontal resolution. So we can't detect anything that's smaller than 30 meters. And then we have 5 meters in the last few years, 1 meter data. We now have half-meter data, and there are military-grade LiDAR, which we don't have access to, which is in centimeters. So as I say, you can see much more detail than you could just 5 years ago. And the old data looks very blurry, and now we're now seeing the Earth's surface and all that detail for the first time. So in many ways, it's like the introduction of air photographs, just over 100 years ago, when people started using surplus warplanes to go up and map. And this is a revolution, if you like, in technology as applied to geology. Excuse me. So this is a LiDAR map of the Toronto area. You recognize Lake Ontario, Scarborough Bluffs, which I've already mentioned, and this very lumpy, hummocky topography in the north called the Oak Ridges Moraine. And there's lots of detail on there that we can see. We can see things like moraine ridges, which are long, skinny ridges. But what we've also noticed, where it says stop 9, is the presence of grooves. And if I can use a pen for a second, you will notice that there are grooves running here. You see a distinct trend in the topography, and they're very clear. Highway 407, if you drive Highway 407 quite frequently, Again, you'll be going up and down ridges, up and down ridges. They're not as large as drumlins, and we refer to them as mega-scale glacial lineations. Very simply, they are long and skinny drumlins. And these have been there all the time for the last 20,000 years, but it's the first time anybody's noticed them. And this is what they look like at smaller scale. So this is 407 in the north, 401 down in the bottom there, and there's 412 if you can afford to use these roads, 407 and 412 that is. But you'll see quite clearly these ridges. They're not drumlins, they have a much longer long axis and they're narrower, so you can refer to them as skinny drumlins. Okay, so what's the big deal? Well, like every other area of the planet, there's more people around than there were 20, 40 years ago. And places that were once remote are now being better mapped, better understood. And of course, these big ice sheets like Greenland and Antarctica are no exception. So this is a relatively recent map, 2011, of the Antarctic ice sheet. And it reveals that the ice sheet is not a simple dome, but has corridors inset within it that are flowing much, much quicker than the surrounding ice. And these corridors are shown in red, and they are referred to as ice streams. Now, that's a bit of an unfortunate word because people always have the connotation that we're referring to water. We're not. We're referring to tongues or corridors of ice within the ice sheet itself, which are flowing very quickly. And they usually feed ice shelves, and you can see two large ice shelves in red. These are the big expanses of red. And the big concern about climate warming at the moment and rises in sea level is that these ice shelves are potentially very unstable, and the ice streams are discharging very large volumes of ice. So there's potential for ice sheet collapse. In other words, the ice sheet will disappear much quicker than it would if it was simply melting. So you'll see velocities, if you look up in the top left there, meters per year of almost 4 kilometers a year, and there's updated information that suggests some of these are flowing at 11 kilometers a year. Now, 11 kilometers a year, you might think, well, so what? But up till now, it's been thought that ice, such as in the Laurentide ice sheet, only flows at a few hundred meters a year. So this is a very big departure from that pre-existing idea about how ice sheets flow. So that's ice streams. Now, that's what they look like. So these are very fast flowing, and they're discharging large amounts of icebergs, and they are usually what we call topographically controlled. That is, they're flowing through quite narrow valleys, and the valleys act like funnels. So you've got the big ice sheet behind it. Ice is flowing out from its center, and it has to flow through these very narrow valleys, and the velocity picks up because you have to discharge much more ice through a narrow cross section. So that's what an ice stream looks like. So the question is, how do we recognize these in the ancient record? And this is an ice study that was done in 2006 by a couple of geologists. And on the left panel, you will see on the top left an area of white, and that is the margin, what we call the terminus of the ice stream. And then in front we have water. And the area that's colored is a map that's produced very similar by a very similar technique to LiDAR. So that is showing the topography of the sea floor underwater. And the assumption is that the ice has retreated, and what you're looking at, that coloured map, is the bed of the ice stream. So this is the sediment that the ice stream was formerly flowing over. And you can see on there long skinny drumlins, which are called megascale glacial lineations. And then on the right there's a close-up, and to cut a very long story short, these are exactly what we are finding in southern Ontario, and as we apply LiDAR data to the whole of North America, they are all over the place. So our understanding of the last great ice sheets in North America has changed dramatically, because we can now use modern ice sheets as analogues, as examples, and identify these ancient ice streams in Canada. And it's all based on recognition of these grooved surfaces and long, skinny ridges, which again are called megascale, large-scale glacial lineations. So that means we can return to our LiDAR data for southern Ontario, and we can actually map ice flow directions, we can map former ice streams, and large features like the Oak Ridges moraine, it now turns out, were deposited between two ice streams. So there's one coming down from the north. If you want the name, we call it the Simcoe ice stream, because it was based primarily by flow through Lake Simcoe. And then there's another one comes up out of the Ontario Basin. The Ontario Basin would have guided ice flow, and it moves up towards the Oak Ridges moraine, and it would have been a large lake ponded between the two ice margins, a lot of sediment dumped in there, and that gives the characteristic shape and morphology of the Oak Ridges moraine. So that's the name of the game, and you'll see drumlins in blue and these megascale glacial lineations, MSGL, in red. And I have a number of students who are progressively going blind, mapping MSGLs across Canada to get a much better idea of the configuration of the ice sheet. And on the right, again, this is an image we've seen before. It's Toronto Zoo. You can see the Rouge Valley very deeply entrenched. And you can see these beautiful groove-like megascale glacial lineations. I take many field trips out with students and the public, and several years ago we visited the ridge at sea there, and it's farmed. This is all farmland, and it's farmed by a family who have farmed it since the 1830s, and they are Mennonites, and I thought I was going to have some problems explaining it. Well, you know, they're farming sediments and landforms that were left 20,000 years ago, but they got very interested, and they said, oh yes, we know these ridges. We refer to them as sweet corn ridges. And I asked why that is, and they said, well, the ridges are much better drained, and we get much sweeter corn grown on the ridges. So they got very interested in the glacial history of the area. So we can map ice streams. This is a simplification of what the area would have looked like. The Horton ice stream, Simcoe ice stream, and there would have been other ice streams coming down the other lake basins as well. And one of the conditions you need for ice streams to develop is you need soft sediment underneath. So the ice can flow much more quickly by gliding, sliding through these soft, wet sediments underneath. So they're ice streams. And we're now seeing the effects of ice streams on hard rock. This is the east side of Georgia Bay, just south of Key River area, and you can see nicely grooved surfaces cut not on sediment, but these are very old hard rocks of the Canadian Shield, about 1 billion years old, And again, we are now recognizing these all the way across Canada and building up a much more detailed picture of the last ice sheet. If you go out in Georgian Bay, this is what you should be looking for: grooves. And these grooves were cut below fast flowing ice. So at the base of the ice there would have been debris, boulders, sand, and it's apparent that the debris is very abrasive and would have cut these grooves into the rock. This is a little bit for you guys in Owen Sound. You have some classic instances of rock that's been cut by ice streams in the form of Owen Sound itself, Colpoys Bay, Dyer Bay, and these have all been cut by fast flowing ice streams called the Huron ice stream that was flowing up and over the Niagara Escarpment. So this is what we call a hard bed. Peterborough, Drummondfield, all the stuff down near Toronto, all those landforms are made out of sediment, soft sediment. Here the ice was flowing off the shield across Georgian Bay and cutting into rock. And you'll see just south of Owen Sound more drumlins, but these are sediment drumlins. Okay, so there's a very nice glacial record in the area of Owen Sound that hasn't yet been fully explored. If you go up to the Manitoulin Island, this is where the Niagara Escarpment and the Kagawong Escarpment, more resistant dollar stone beds within the Paleozoics, have been really streamlined by fast flow. And you'll notice the presence of bullet shaped rock masses on the edge of the escarpment. It's a very serrated edge to the escarpment, and this is simply reflecting streamlining by very fast flowing ice with highly abrasive sediment at the bottom. This is data which is hot off the press. This is LiDAR data which has just been recently collected from near Kingston. And you'll notice grooved bedrock surfaces, particularly up near the Arrow. And this is entirely the product of fast ice flow over limestone. These are very flat limestone plains, and they have been extensively grooved by fast ice flow. You can see Highway 401 there for scale. Along Highway 6, there's nice cross sections along the side of the road through these grooves and ridges. So there on the top left, there's a plan view, LiDAR data showing the bedrock topography. And then in the lower part, there's a student standing in front of a groove cut in the limestone surface. So the big deal here is that it's more evidence of fast ice flow and the presence of ice streams in Ontario. We've extended that mapping as LiDAR data comes in. We're now going down into New York, and the white arrows on here are major ice streams that we've identified. And again, it's all on the basis of these mega scale glacial lineations, and the story here is again one of topographic confinement. So ice is flowing down from Quebec, Labrador, and it's forced to flow between the Adirondack Mountains, Catskills, and so on, and the Canadian Shield, the Algonquin Highlands, and velocity picks up, and then it goes down the Mohawk Valley as well into the Hudson, and then goes down into the Finger Lakes. And I wasn't going to talk about the Finger Lakes, but they've always been a bit of a puzzle for geologists, why they have that shape, how they evolved, and guess what? It now looks as though they were scoured out by fast-flowing ice streams. And also possibly Lake Ontario. It's a very deep water body, and the deepest part is in the Rochester Basin. And the unusual thing about the Rochester Basin is that its depth is way below sea level. It's 244 meters below sea level, which is very unusual. Rivers can't cut below sea level because they are graded to sea level. So again, we're now starting to think that this is all the product of fast ice flow, simply because the ice streams are very, very effective erosive agents. So this is an image from upper New York State, just north of Seneca Lake, and you can see drumlins in the top. These are really exquisite detail, and the thing we're now exploring is that drumlins actually evolve into megascale glacial lineations. So you can see drumlins at the top there, the bullets, the upturned rowboats, and then you'll notice that there's a sort of intermediary landform. It's slimmer, not quite as long as the MSGLs in the south, and this is a proxy for ice flow velocity. So we think drumlins are probably what we call steady state ice flows, a few hundred meters a year, and then the ice velocity is picking up and becomes streaming flow. So this offers the possibility of being able to map locations of ice streams, and also, most importantly, get some idea of ice flow velocity. So it's an important step in much better understanding of these big ice sheets. And it's all fundamentally dependent on LiDAR, better imaging, and using analog information from modern ice sheets. We've done the same thing for the Cordilleran ice sheet out west. And we've identified, I forget the number now, 12, 13, 14, 15 different ice streams within the Cordilleran ice sheet. The limits of the ice sheet are shown as the blue, heavy blue line. And again, the story is that the ice is building up over interior plateau, and then the ice is flowing out through valleys to reach the coast to the west, or the interior to the east. And again, you get topographic forcing, where valleys are acting as funnels, and a lot of ice is being forced through those narrow orifices, and the velocity picks up. So it looks like the Cordilleran ice sheet was very similar in its major structure to the Laurentide ice sheet. And this is a LiDAR image from near Seattle. And again, exquisite detail of the bed of the former Puget Sound ice stream. And you can see drumlins, you can see grooves, you can see MSGLs. So this is what an ice sheet does, a fast-flowing ice sheet does to its bed. And it's quite interesting. You can get into this into a lot of detail, and there is an engineering field called tribology, which is the study of friction and the frictional wear of materials. And it's a huge area. Friction robs GDP of something like about 3%, so it's well studied. And the most efficient surface, if you were to take your car to pieces, I don't recommend this, but look at some of the bearing surfaces, you will notice that there are grooves, there are engineered grooves on those surfaces. And this is the most efficient type of texture, and it reduces basal drag, it reduces friction. So we now think that this is the ice sheet basically engineering its bed, and we're now applying a lot of tribological studies to ice sheet flow. If the ice is going to flow fast, it has to reduce the relief of obstacles on its bed. So we go from drumlins, which are quite high, you'll remember that photograph I showed you before, to these MSGLs, which are long, skinny drumlins. And we think that the drumlins have lost weight, as it were, by erosion as ice velocity picks up. And that is an area called paleoglaciology. Paleo means old. So if you want to become a glaciologist, you go and look at modern ice margins, modern ice sheets, and then if you want to look at these ancient ice sheets, that's paleoglaciology. So the story I have this afternoon is all about ice age streams, not ice age creams. So this is a new map, relatively 2018, of the Laurentide ice sheet with ice streams. And guess what? It's already fundamentally out of date, because as LiDAR data is collected almost on a weekly basis, and I have students who are scouring the planet for good data sets, the number of ice streams, which are shown here in dark blue, has increased dramatically. And I haven't counted up the total shown here, but I would say it's doubled since 2018. So the whole mode of flow, the whole glaciology of the ice sheet was dictated by ice streams, just as we saw in Antarctica. And that solves the puzzle, because this big ice sheet, as thick as it is, disappears very, very quickly. So it's at its maximum 20,000 years ago, and it's largely gone by 10,000 years ago. And people have said, well, that's pretty quick. There's an awful lot of ice. The climate's still not that warm. How can the ice melt that quickly? And it's always been a puzzle that's bothered glaciologists, paleoglaciologists. And of course, if you've now got these fast flowing ice streams, you're pulling enormous great volumes of ice out of the ice sheet. It's not sustainable at all. Ice sheets grow and are nurtured by snowfall in the winter, and you can easily calculate that the amount of ice that's discharged along these ice streams far exceeds the accumulation rate every winter. So this is an ice sheet, that's dying. And we now begin to realize that ice streams are the characteristic hallmark of ice sheets that are on their deathbeds. So this is what an ice sheet looks like as it's just about to expire, which is not good news if you look at the modern Antarctic and Greenland ice sheets. Right, LiDAR data. So, we're looking at megascale glacial lineations, we're looking at drumlins, but you happen to notice a lot of other stuff. And this is down near Kingston, Highway 49, just south of the 401. And you can see a lot of grooves on this surface. They're not straight, they go in different directions. And these are produced by icebergs floating in a glacial Lake Ontario. So the top diagram, little cartoon there, shows the ice stream retreating. Now I said that they flow very fast. That means they carve, that is, they break off huge amounts of icebergs from their margins. So this is what we see exposed on the former floor of glacial Lake Iroquois, a whole bunch of iceberg scours, icebergs that are floating, and they are pushed by wind or currents into shallower water areas, and they scour the subsurface. So if you go up to Canada's Arctic, up to the Beaufort Sea, that's what the modern sea floor looks like as a result of scour by seasonal pack ice and so on. But this would have been a very widespread process in the lakes too, as these ice streams disintegrated at the end of the last glaciation. So these are about 12,000 years old. And again, they were seen on air photographs earlier, but the number of them was completely underestimated. Now, this is an interesting application of LiDAR too. This is bedrock surfaces. There's no glacial sediments here at all. But these are newly discovered faults near Kingston, and these are breaks in the crust, and you can see them quite clearly exposed. So again, LiDAR has all sorts of applications to what we call structural geology, which is looking at how rocks bend and break. And there's also an area of geology called neotectonics. Don't forget that the North American plate is moving all the time by about the thickness of a piece of paper a day, or about 4 centimeters a year, and that drift towards the west creates stresses in the rock, and they break. And there's a lot of interest in the extent of neotectonic activity in Ontario, because we do have this thing at Pickering, which is a nuclear power plant. So this is another application of LiDAR to structural geology. You can very easily generate 3-dimensional topographic maps. This is up near in the Kawartha Lakes. This is what we call rubble terrain. There's a scale there on the left-hand side, and it makes it a lot more easier to visualize what's going on in terms of the landscape. Some of you may be familiar with the Dummer Moraine. It's an area of very rough country, big boulders. Al Purdy wrote a famous poem called The Country of Our Defeat, when early settlers went up there and tried to farm this and basically gave up. And this is a product of these ice streams plucking at bedrock, ripping it apart. So you can see a white arrow on there which has got ice flow direction, and all this rubble terrain is in the lee side, the down ice side of the obstacle. And again, this was completely unknown until about 6 months ago. We're now mapping this across Ontario. Right, so let's put this in some sort of perspective, this LiDAR revolution, because geologists are basically scavengers. They go out and travel, usually at somebody else's expense, and look at the landscape as an indication of what might be below it. And there have been previous revolutions in geology. The first one, the oldest one, is the world's first geology map. This is an absolutely incredible document. It's on a papyrus roll, something like about 11 meters long. You can see part of it in the the Egyptian Museum in Turin, northern Italy. And we know who produced it. It was ascribed to Ramses IV, and Ramses IV was not only a pharaoh, but he was also a geologist. The ancient Egyptians were fixated on rocks. Many of our names that we use for rocks in geology come from Egypt, and people have gone back in using LiDAR and remap this area. This is from a famous wadi, Hammamat, which had gold mines in it, springs, quartz veins. And this work has shown that this map, 3,000 years old, is very accurate. So that's the world's first geology map. Then, of course, William Smith's famous map of England and Wales, 1820. What's been called the map that changed the world. I think that's somewhat inappropriate because the Egyptians had got there first 3,000 years ago, but that's a matter for another time. And then, of course, closer to home, this is William Logan and his geological map of Canada in 1864, at least what was Canada in 1864. So these are milestones in geological mapping. And we are right in the middle of another revolution right now in terms of LiDAR mapping. And I'm going to get out the way so you can read the caption, but the future maybe is not that bright, actually, because I have several students who are working on using artificial intelligence. There's a lot of computer programming. These are the steps up on the right there, so don't worry about them. But LiDAR and digital data now allow automated mapping. So basically a computer can be trained to recognize certain features. And this is a map that we've produced from Upper New York State. It's in regard to glacial geology, but it could be anything, where we've trained the computer to recognize certain landforms. And these are early days yet, but this will expand. And the mapping of Canada took something like about 100 years to do. And I think in the next few years, remapping will be done virtually instantaneously at the moment that the data is collected. So you can see how revolutionary this introduction of LiDAR is to geology. So I'm going to wrap up my presentation right now, and if I haven't put everybody to sleep, I'll invite questions. Okay, so thanks for listening. You've been a very attentive and very quiet audience. Thank you.